This is a short introduction to sampling and something called the central limit theorem, which is both subjects actually are both key subjects in statistics and understanding data. And the first is really a subject in terms of a very practical nature. The second, the central limit theorem, is something that permeates all of sort of classical, what I call classical statistics. And so we'll talk about both of them in a very concise way. Let's start with sampling. Now, one of the key things with the body of knowledge of statistics is to move from what I would call sample to population. So in the picture that we see up on the screen, you can picture the blue blob as all of the population. Could be population of people in the United States, but it could also be a population of potential phone calls that could be coming into a call center, or the population of candy bars that are made at a certain factory. The point of that is that whenever we take data, or almost all the times we take data, we don't take the whole data set, but we sample from it. And that's true even if we take essentially an entire lot, because, especially in production, because we want to generalize to future states of the population, not just today. So, so that's what statistics is really the tool. Statistics and probability is the tool and the body, the subject that can really help us understand that to the highest degree that we know of. So again, we go from the samples, which we see, to the population, which is what we really care about. That's really the essence of statistics. And later on, in a later lecture, we'll talk about how the building blocks of all the statistical testing that we do are really based on these four things. And if I boil them down, I'd really X out the median. But they're based on the mean. Simple testing is based on mean, which takes us from the sample mean to the population mean. The standard deviation, which takes us from the sample standard deviation to the population standard deviation. The sample median, or the 50th percentile, which takes us to the to the median of the population, and finally a proportion of good, a proportion of bad, or proportion of people that prefer Pepsi over Coke. That takes us from a sample all the way to the population. So that's really what we're looking at. Is statistics helps us bridge the gap from the left to the right. But to do that, whenever we take a sample, unfortunately, samples are not perfect. They don't tell you everything. So there are things that statisticians call errors that creep in. Errors really are just uncertainty, and it's a very unfortunate name, because when statisticians talk about errors in data, they're not necessarily, or even uncertainty, they're not necessarily talking about people making mistakes like goofs, judgments, or miscoding data, fat-fingering data, anything like that. No, what we're really talking about is inherent sampling, inherent errors, or inherent uncertainty that is in the sample, simply because there are many more members of the population that's out there, and we acknowledge that there's a chance that we chose a logical sample, even if we chose it randomly, which is the best way of doing it. Proper statistical sampling, as we say here, it adds no bias to our data set. That doesn't mean that it ends up being a completely representative sample, but it's the best shot that we've got. Now, there's two basic ways to control sampling error, and probably the most straightforward we'll explore right now, and that is increasing the size of the sample. Later on, we will explore stratifying, or one other strategy is stratifying a sample to eliminate some of the inherent variation between groups. There are other ways that you can do this in design experiments, which we'll learn about later. Right now, we're going to look at this by increasing the size of the sample, and what happens then, and how is it all related. All right, so the two building blocks of statistical inference are things called hypothesis testing and confidence intervals. Now, hypothesis testing, I have found that people usually find that to be incredibly unintuitive. However, confidence intervals are not. A confidence interval is simply, and let me draw this for you. I can get the tool open. Oh, goodness. There we go. Struggling to get the tool open. There we go. Let me draw this for you, and I think you will find this, I hope you'll find this helpful. So confidence interval is simply this. If we make an estimate of a quantity, whatever that quantity is, how much a car repair will cost, or the height of a tree, or something like that, or the amount of time that a project will take to finish, all of those things, if we make an estimate, very often if we're intelligent about it, we'll add a cushion on it, a plus or minus, and draw this here. Oh boy, that's terrible drawing. Well, using the tool for that ends up being terrible anyway. We'll add a plus or minus onto it. So if you can think of that right there being, say, our time estimate, our central estimate, people call it, a statistician would call it a point estimate. We simply add a little bit plus and a little bit minus, and usually those are the same amounts to that. And the confidence interval then is this whole piece where we would say, well, we're confident that the true cost of the project will be between, say, I don't know, $45,000 and $60,000, let's say $65,000, instead of simply saying, well, it's going to cost $55,000. So we're hedging our bets a little bit. Well, if you want to do this using statistical methods, we actually put confidence on that statement as well. But usually we're talking about the margin of error. Okay, so that's really what we're talking about. And it turns out that when you increase the margin of error, when you increase your sample, you decrease the margin of error. It's really as simple as that. We know that intuitively. If we take a sample of, say, 9 people, and we want to know the average height of a male adult, well, if we looked at one person, and that would probably not be a good estimate. But if we looked at 9 people, if we sampled 9 people, that'd be a much better estimate. In fact, if we sampled 100 people, that'd probably be actually pretty darn close to the population average. And that's exactly what we're seeing. What statistics can tell us, and the central limit theorem will tell us, is how much it actually decreases as you increase the size of that sample. And in fact, the statement is this. The statement is actually pretty straightforward. It is right there. It decreases that. Here's what the margin of error is. See this little equation right there that looks like T, confidence level, times S over N. That's simply another word for the margin of error. All that stays basically the same as you increase the size of the sample. Not quite, but almost. And when you increase the size of the sample, that denominator gets larger, and so this ratio, S divided by N, gets smaller. And you shrink, basically, your margin of error by the square root. So the good news is you can do it, but the bad news is that you get decreasing, as you increase the size of the sample, your margin of error decreases more and more slowly. To think about this, think about if we wanted to decrease not the size of our sample, decrease the margin of error from, say, plus or minus 2 to plus or minus 4, we'd have to double it. But if we wanted to decrease it again by a factor of 2, to go from plus or minus 4 to plus or minus 2. If we wanted to go from plus or minus 2 to plus or minus 1, we'd have to decrease it another factor of 2. So we're already multiplying by a factor of 4 the original sample. And you can see that if you want to decrease it by a factor of 10, you're talking about increasing the size of your sample 100-fold. That's huge. So anyway, and there are statistical tools that can help you calculate what that would be. But you can see that there's the bad news on all of this is that there is a decreasing value of increasing your sample size. It just doesn't keep happening. So let's take a look at that from an example. An example in the book, we're actually going to use a tool called Sample Sizer, which is available through Straightline's website. I'm just going to go ahead and open that up. And the example we'll do is very similar to the one in the book in front of you on slide 101. if you're following along. So suppose you wanted to measure a baseline of some process, and suppose it was a cycle time of how long the process took to finish. Let's just walking through. You notice that there's a number of other scenarios that sample sizer can help with. Let's go on to step 2. Let's call our measurement cycle time. And let's say we measure it in minutes. That happens to be a number, a numerical type of variable. And then let's say that we're only really interested in the average. Let's forget about this sensitivity, which is kind of the spread, if we're interested in the variance or the standard deviation. And let's say that we had some sample size will let you do it in percentage of range. But let's suppose we had something specific in mind, and we wanted a plus or minus 2-minute margin of error. And we didn't know what the standard deviation was, which is fine. Most people don't. But we did know that typical operations gave results between 3 and say 30 minutes, not 39, 30 minutes. Typically, this process completed in somewhere between 3 and 30 minutes. How many samples would we need to take to have a margin of error of plus or minus 2 minutes if we were sampling? Let's take a look at what that is. Let's hit the continue button. And here we are. It's actually pretty surprising how few samples we really need. And there it is right there. You can see that. Now, we're not that interested in the spread, so I'll take that off there. I'll move it away. But you can see that we only need about 19 samples if we want to get an average to within plus or minus 2 minutes. And that's it. Now, if we wanted to within plus or minus one minute, if we wanted to within plus or minus 1 minute, my theory is that we're going to have to quadruple that sample size. So let's take a look. And there you go. In fact, it turns out that it goes from 19 to about 78, which if you think about it, 19 is about 20. 20 times 4 is 80. So to cut in half that margin of error, we have to quadruple. Right? Factor of 2 means a factor of 2 margin of error means a factor of 4 increase in sample size. And there you go. There it is right there. We went from 19 plus or minus 2 margin of error to when we wanted a plus or minus 1 margin of error, 78. So there you go. And if you want to go to a half, guess what? It'd be another multiple by 4. So you can see how when we're shrinking our margin of error, we have this diminishing return, and the cost really goes up. We have to take more and more samples. All right. Hopefully that illustrates a good point. And you can use this, by the way, if you want to. This isn't a demo for the software, but it just shows you can do very quick calculations with this. You can do more complicated problems than that too. All right, so we've established essentially something that's very similar to this formula, that if you want to decrease the margin of error by cut it in half, you have to quadruple the sample size, which is an interesting and maybe an important rule of thumb to kind of put in your brain. Okay. All right, so let's move on now to, because of this, there are some interesting implications, and let's move on to the central limit theorem, which is one of these things that's a real underpinning of statistics, and it's one of the reasons why, though many people talk about how everything needs to be normal before we use our tests, that's actually not true, and that many standard tests, the t-tests and two proportions test are the ones in particular, are very robust to departures from normality. And we're going to show that. So there's something called the central limit theorem, and it simply states this, that if I have some parent distribution, say x, okay, and that might measure the actual cycle times of the process that I was talking about before. Again, it could be a process of people walking through a medical practice, or it could be a process of people waiting in a bank. Either one. But if I have a parent distribution that is, say, some distribution, could be log normal, could be anything, could be skewed, that if I take a series of averages, let's say every half hour I average the wait times of all the people who are going through that transaction, that those series of averages will actually be normal. And not only that, but it says even more, that that distribution of the sample averages will be normal with the same mean as the underlying population, and this is the kicker, that the spread on that estimate, or those averages, will decrease by the square root of n, just as our margin of error did. So it's very similar. They're all kind of related sort of things. All right. So let's take a look at that. I'm gonna draw that out for you before we go into the into a spreadsheet where I'm going to just kind of substantiate that for you. But let's draw that out. So again, if I have some distribution x, let's say x is cycle times of a process of a some transactional process. And just for fun, let's say it is the process of ordering dinner and having it brought to your table. Right? So the cycle time is that measurement of the time it takes between when you order and when you get it at your table. That's what we're calling the cycle time. Okay? And let's say we went to a particular restaurant and we found that the distribution looked like this. If we looked at the times, they looked like this. Okay? Certainly not normal. In fact, we would say it's skewed to the right. So these were cycle times. And here's my frequencies. Right? And in fact, but what I would say is let's say we got enough so that we could estimate it's some distribution. I'll say that's SD. No, that's not a good notation there. SD is not good notation. Okay. Let's say that this is X, and that X was something that was any distribution. And it has some unknown mu, unknown average, and unknown standard deviation. But it looks like this. My claim is that X bar will look normal. It will be bell-shaped, and it will have the same distribution as this, and it will have almost the same standard deviation, but it will be divided by the square root of the number of samples that I take. If I say, let me average, I take 3 measurements every hour, or let's say it takes 16 measurements every hour, and I average those, and I look at the distribution of those, that distribution will look like this, with a very specific mean, the same one, and the spread of this distribution, the standard deviation, which is given right there, will be the standard deviation of the bar, of X bar, will be equal to the standard deviation of X divided by the square root of 16, which in this case would be 4. Okay? So let's actually go through that example, or go through an example and see how that works. Now, I'm not going to prove this mathematically, but what I'm going to do is I'm going to give you a bunch of examples that will illustrate that this actually is true. The proof is interesting, but it's not a necessary thing for most black belts. If you want to be a mathematical statistician, you need to know it. This lecture is not for mathematical statisticians. So let's take a look at that. Okay, so what I have here is on the left-hand side, I've got what I call the population, and that's 1,000 data points. So it's not quite infinite, but it's very, very big. And over on the right hand, I've got 16 points that are taken randomly for that. Now, it's no surprise that if we have a parent distribution that is bell-shaped, that our samples are often bell-shaped. But look, not always. So if I continue to take another sample, that's pretty bell-shaped. That one, yeah, a little bit. That one, yeah. That one's not very bell-shaped. You can see that's part of sampling. You'll also notice that in my parent distribution, I've got a mean of 5 and a standard deviation of 1.12, which is, or 1.19, which is about 1.2 which is about 1.2. But in my samples, I don't always get those numbers, sometimes a little bit less, sometimes a little bit more. Let's just focus on the mean here and see if we always get 5. Clearly we don't, right? Sometimes a little bit lower, sometimes a little bit above. And the standard deviation varies quite a bit. So you can see how that happens. My claim, however, is that the sample mean, that is, if I take the average of these 16 and I look at the distribution of that over and over, that distribution is going to be, that distribution for this case is going to be about, if I look at x bar, that distribution is going to look normal with a mean of, in this case, 5, and a standard deviation of, I'm going to call this 1.2, of 1.2 divided by the square root of 16, right? But the square root of 16 is just 4. I'll write it. I'll be rigorous here. Or, in other words, x bar is normal 5, comma 0.4. 0.3. I'm sorry. Right? That's 0.12 divided by 4 gives me 0.3. Let's see if that's actually true. What we're going to do is we're going to take, at this point, we're going to take a look at the distribution of means. So let's mosey on over. So every time I click a sample here, what we're going to do is draw from that same population and plot it up here. So here's the plot as it's going out, and here's the frequency chart. And just for fun, I'm going to show a normal distribution on there as well. And we'll see if it has a mean of 5 and a standard deviation. Oh, I said 0.3. That's pretty close, yeah. Well, the first one didn't quite do it. It's a little bit low. That's no surprise, so it doesn't quite look normal yet. Let's look at another one. And another one. Another one. That's interesting. It's already converging pretty quickly. And you can see as I do this over time that not only is the shape getting normal, but check out where the mean and standard deviation are. It's exactly where we thought it was going to be. I'm going to let this rip for a while. I'll let go to, say, 100 or so. There we go. And you can see it's very normal, right? And look at that. This mean and standard deviation almost exactly the same as what we predicted. Pretty cool. Now, you might say, well, we started with normal. No surprise that we ended up with normal. Let's move back here. Actually, let me take a look at this. I'll reset it. And what we'll do is we'll look at other distributions. Because remember, the claim was that it was any distribution. So let's look at something that clearly is not normal. Nobody on Earth would say that's a normal distribution. And in fact, when we take a sample, in this case, we're looking for one that's a mean of 5, standard deviation of basically 2.9, about 3. We'd claim that the sample mean would have a mean of 5, standard deviation of a little bit less than 1. Okay, so let's take a look at this when we take a sample. It certainly doesn't always look flat, but no way is this looking normal. Let's take a look at the sample means. The claim is that this is going to end up looking normal. Let's see. Well, so far so good. Well, it looks like what it was going to. Let's let it rip for, say, 100 or so. Oh my goodness, look at that. We did end up with something that looked very normal. Look at the mean. 5, standard deviation, it was supposed to be 0.732. Look at that, 0.762. So it turned out normal after all. Let's look at one more example. Look at something that really is not normal. Oh, well, let's look at our friend, the skewed distribution. Okay, and do the same thing. Again, the samples don't look normal, but do the means look normal? That's the real question. Let's let it go. Now, it does take a little bit longer for the skewed distribution, which is interesting. The farther you start from normal, or from symmetric, really, the longer it takes you. Now, notice, we didn't get exactly normal, but clearly we're getting there. We're getting there, and look at the mean and standard deviation. not at all bad in terms of how close it is. All right, we'll look at one more. This is just too fun. Let's look at U-shaped. Again, no way is this normal. But and really the trick is that anytime it's symmetric, you're going to get something converging very, very quickly. When you have a skewed distribution, you may have to up the number of samples a little bit. I'll show you what happens when we up it to, say, 36, which would be square root of 6, right? Or square root of 36 is equal to 6, I should say. Okay, let's take one here and let's see if it works. Wait for 100 of them or so. And again, look, very normal distribution, and we got exactly what we predicted. Okay, so I did want to show you the last time. If we have a skewed one, we may have to take more samples. So in this case, we'll go up to, say, 36. And taking more samples than your average is going to make it converge pretty quickly, or more quickly. So if we look at the distribution of means, now my claim is it's going to be more normal quickly, more quickly, more quicklier. There you go. There's my 100 before. That looks a lot more normal than the one where we were only taking 16. And that's just because if it starts out asymmetric, it just takes a little more oomph to push it to be normal, to push the means to be normal. And there you have it. So even though this is intuitive that we have, it may not be intuitive, the numbers here, but even though it's intuitive that we, when we average something, our average gets better and better and better as we increase the sample size. Now we know why that's true, and that our estimates and how quickly it gets better when we increase the when we do increase the sample size. So hopefully you found this illuminating, and just a very quick as a very quick recap, we talked about two things that were basically the same. Or very, very similar, and that was that we talked about sampling, and we found that for confidence intervals, usually it had some sort of thing like it was we were estimating a point estimate plus or minus some margin of error, and that margin of error was a function of something, usually S, our variance. It was a function of S divided by the square root of N, which was the number of samples. N is number of samples. Right? So because it's a square root, you have to quadruple something to get it halved. To get this margin of error cut in half, you have to quadruple the sample size. Okay? That's the first thing. And the central limit theorem, the CLT, by the way, this is only one of many CLTs, but the central limit theorem says that if I have X from any distribution with a mean of mu and a standard deviation of sigma, that the distribution of averages from that distribution, if I take 10 and average them and I do that repeatedly, that distribution will be normal with a mean that's the same and a standard deviation that's, call it X, and a standard deviation that's almost the same, but it's shrunk by a factor of the sample size that you're averaging over. And that's good to know. That's not coincidence. That's that same factor that's right there. So anyway, that's it, and hope you got a lot out of it, and you found that the demo was fun and amazing. All right, take care. Talk to you later.